Alright, so you're welcome to this week's class. This is Dr. Yahya. So today we'll be solving the Schrodinger wave equation. In our last class, we were given wave function and we are asked to calculate the potential energy. I think that was what we solved. But in many real life cases, what you will be given is the potential. Okay, you know the Schrodinger equation. Let's say the one-dimensional. So the one-dimensional time independent Schrodinger equation is minus h bar square over 2m d square psi dx squared plus v psi equals e psi of x. So this is one-dimensional Schrodinger. So what will be given in many cases is that you'll be given this potential, then you'll be asked to calculate the wave function and the energy. So that's so that will be a boundary value problem. Okay, so in quantum mechanics we say that's a bound state problem where we have to solve the wave function and the energy. Okay, so and that is what we're going to do today. So we're going to solve this Schrodinger wave equation for a simple problem, I think the simplest problem, and we'll calculate the wave function and the energy again values. So let's take the example. Okay, so this example, a particle of mass m, the mass of the particle is m, is trapped in a one-dimensional box with a potential described by v of x equals 0 when x in this range is between 0 and a, and it is infinity otherwise. So we can sketch a graph of this potential. So let's start with solution. So let's say this is our axis. So the potential is trapped between 0 and a. So x is between 0. So this is 0. And let's say this is a. So this is x-axis. And this is the potential. So the particle is trapped. This is an infinite square wave potential. Let me use red. Okay, so the particle is between this, is inside this box. We are told that the outside this box the potential is infinite. Okay, so it means the wave function outside is 0, so the particle is not there. So the particle is within this box. So anytime the potential is infinity, so it means the wave function is 0. So there's no particle, so there's no need to worry yourself about that region. So outside this region, painted in colored in red, so the potential, the wave function is 0. So the wave function is 0 after this region. Okay, but inside this region, the particle, the wave function is non-zero. Okay, the particle can be found within this 0 and a in the box. So this is a one-dimensional box actually. Okay, so how do we solve this problem? So we have to use the Schrodinger wave equation, and the Schrodinger wave equation, we have written it up here. Okay, minus, but let me rewrite it. So we have minus h bar squared over 2m the square psi the x squared psi of x plus v of x psi of x equals e psi of x. So let me call this equation 1. Now in this case, we said we were told that the potential is 0 between this 0 and a, so we are interested in this box. Outside the box we are not interested because the wave function is 0, so we are only interested in the box, inside the box. So the particle is trapped inside the box. So v of the potential is what? Is 0. So all we need to do is to substitute 0 for the potential, so that we have minus h bar squared over 2m the square psi of x dx squared plus 0. Okay, So plus 0. So the plus 0 is 0. So that will be equals E psi of x on the right hand side. So let's call this equation 2. Now we can bring equation 1, the left hand side of equation 2 to the right hand side, or we can bring the right hand side to the left hand side. So in essence we can write, so any one that we do, we can write h bar squared over 2m the square psi of x, the x squared, plus E psi of x. So let's call this equation 3. So you know this minus, not this minus, if you include this minus here, then this E psi, when it gets to the left hand side, it will be negative. So you can divide through by negative so that you have this equation 3. Now we can divide through, so divide divide equation 3 by h bar squared over 2m, or multiply by 2m over h bar squared, anyone. So if you multiply by 2m over h bar squared, then we have the square psi of x, the x squared, plus, so we are multiplying by 2m over h bar squared, E psi, okay, of x, so equals 0. So let's call this equation 4. So this 2m over h bar squared, so 2m over h bar squared, we want to denote it by k squared. Okay, so let's denote, so let 2m over h bar squared be denoted by k squared. So please, we need to save this. So let me call this equation 5, because we're going to use this later. Okay, we're going to use this later. So let me also circle it. So in that case, what will happen to our equation 4? Equation 4 can now be written as, equation 4 can be written as the square psi, the x squared, plus k square, sorry, 2me. So k square psi. So let me, so you should take note, it's 2me, 2me. So it covers E. So because the energy is also a constant, it's a value, it has a value. So 2me over h bar squared. So let's represent that, so that we have only psi as a function. Okay, as a function. Okay, so we now have, so we represent 2me over h bar squared by k squared. So we now have this equation 6. So the square psi of x, the square psi is x squared plus k squared psi. Now, so this is the equation we're going to solve. So how do we solve this equation? So this is a very, very simple second order homogeneous second order differential equation, and I believe you have been taught in mathematics classes how to solve this problem. But let me just digress a bit. So how do you solve this type of problem? So usually, if you have in mathematics, if you have let's say an equation, let's say a the square y dx squared plus b dy dx plus c y equals 0. So this equals 0, sorry. Yeah. So if you have this, what you do is you form an auxiliary equation. The auxiliary equation will be a m squared plus b m plus c equals 0. So you now solve this quadratic equation. After solving the quadratic equation, if you get real and different roots, that is, you get maybe m1 equals 2 and m2 equals 5, okay, as the solution to this auxiliary equation, then in that case the solution to y will be a exponential m1, that's the first root x, plus b exponential m2, which is the second root. So this will be your solution when you have real and different roots. What if you have, after solving your auxiliary equation, So let me say, so this is case 1. So case 2, you can have the case whereby you have real and equal roots. Your roots are real. So let's say, for example, in this case, m equals 2 and m2 equals 3. So we have, this is the solution. So what if you have your roots are real, but they are equal? They are equal. So m1 equals 2, m2 also equals 2. So we can say m1 equals m2 equals a constant m, okay, which is 2. So in that case, your solution will be exponential the root, okay, so maybe m1 or m2 or m, then x, then into bracket a plus b x. So these a and b are constant, and they are determined by the boundary conditions. They are determined by the boundary conditions. So for quantum mechanics, I'll tell you about the boundary conditions when we get to solving the problem properly. So the case 3 that you can have when you solve the auxiliary equation is that you can have a case whereby the roots are complex roots. Complex roots in the sense that your m is maybe 2 plus 3i, that's m1, and m2 is maybe 2 minus 3i or 2 minus 8i or so. So they are different, but they are complex. They are complex roots. So anytime you have complex roots like that, then the solution of the equation will be exponential. So this is the real part and this is the imaginary part. So the real part, imaginary. So exponential, the real part, which is alpha, x into bracket a cos the imaginary part x plus b sine imaginary part x. Okay, so it doesn't matter, you can write it like this, you can also write it in this form: a sine the imaginary part plus b cos imaginary part. So but what will determine the values of a and b are the boundary conditions. So this alpha is the real part of the solution and beta is the imaginary part of the solution. So let's get to our own problem. So in our case, we have equation 6. So let me write equation 6 again. So we have this square psi, this square psi dx squared plus k square, I think, plus k square, plus k square psi of x equals 0. So this is equation 6. So how do we solve this? So again, what we do is we create the auxiliary equation. So it will be m squared plus k square equals 0. Okay, m squared. So this is square. Okay, there is no this side dx. If you had the side dx, there would be plus m. Okay, plus m. But there is no the side dx. We only have psi. So that is a constant. So k squared equals 0. So we now solve this. If you solve this, we have, so this can be written as m squared equals minus k squared. So if m squared equals minus k squared, it means m equals plus or minus square root of minus k squared. So you have to take note, we have plus or minus square root of minus k squared, not square root of k squared. But we can easily write m to be plus or minus square root of minus 1 multiplied by square root of k squared. So what is square root of minus 1? Square root of minus 1 is I. The square root of k squared is what? Is k. So the solution is that our m equals plus or minus ik. What does this mean? It means that m1 is plus ik while m2 is minus ik. So the real part, in this case our own alpha is 0, our own beta is what? Is k. So that our solution, our psi of x, will be either cos exponential first. So exponential first. So exponential, the real part, in our case the real part is 0, so 0 times x into bracket a sine the imaginary part, our imaginary part is k, so kx plus b cos kx. So this is what we have in our own case. Okay, so of course exponential 0 is what? Is 1. 0 multiplied by x is 0. So exponential 0 is 1. So that we have psi of x equals a sine kx plus b sine plus b cos kx. So let me call this equation 7. So now I told you that to determine this constant a and b, we need to use the boundary conditions. Okay, so our own boundary condition is that if you look at, let me plot the potential again. So this is our potential, so this is x and this is v of x. So we drew our potential as this. So this is a. So this is 0 and so this is 0 and this is a. Okay, so and we say that outside this potential, the outside this box, the potential is infinite. It means that the wave function is what? 0. So what we must do, this is a boundary value problem. So what happens at this boundary with inside the box and outside the box, they must be the same. So since outside the box the wave function is 0, so it means at this boundary inside the box the wave function must also be 0. The same thing with this point. So the psi at a must be 0 and the psi at 0 must be 0. So at the boundary, okay, so it must be 0 also at this point at when psi of a must also be 0. So these two are our own boundary condition. That is for this particular problem. So if you have another problem, you can have a different boundary condition. Okay, so in that case it means we say psi of 0 equals what? 0. So that would be a psi of 0 means when x is 0. You know, psi is, it depends on x. So it means when x is 0, so it means sine k times 0, which is 0, plus b cos 0, and the answer is what? Is 0. Now what is sine 0? Sine 0 is 0, so it means a multiplied by 0 plus b multiplied by what is called 0? 1 must be 0. A times 0 is 0, so it means b of 1 equals what? 0, which means that b equals 0. So if b is 0, then what will be our function? Then our function, which depends on x, will be a sine kx. Since b is 0, so it will be 0 multiplied by cos kx. Okay, now in that case, let me call this equation 8. We have applied one boundary condition, so let's apply the second boundary condition, which is psi of a equals 0. So psi when x equals to a. This one is psi when x equals 0. So psi when x equals to a is also 0, which equals a sine kx, but x is now what? X is now a, and we say this is also 0. So it means we have a sine ka equals 0. If you have a sine ka equals 0, what are the two possibilities? Two possibilities. So let me write here two possibilities. The first possibility is that we say sine ka equals the first possibility is that we say a equals 0 over sine ka, and a equals, if a is 0, it makes no sense, because if a is 0, this wave function will be totally 0. If wave function is 0, then there's no particle present, so we are not interested in that. This is physics. That's why physics is different from mathematics. So we have to look at the physical implication. So if a is 0, it makes no sense. So this makes no physical sense. So this makes no physical sense, because the particle cannot be found. Because the particle cannot be found anywhere. Okay? Because the particle cannot be found anywhere. Now the second possibility is that, so this possibility one is that we say sine ka equals 0 over a. So and that one makes sense. So in that case a is not 0. So the second possibility is what we choose. So we have sine Ka equals 0 over A, which is 0. So if sine Ka equals 0, it means Ka will be arc sine of 0. Now, what is arc sine of 0? So arc sine of 0, let me clear. So arc sine of 0 is 0. Okay, but it is not only 0 that can give us sine 0. If you find sine 180, it will give us 0 as well. If you find sine 360, it will also give us what? 0. So so we can have, so this Ka can be, we can call it 0, we can call it 180 degrees, 360 degrees, and so on and so forth. So this is 0 in radian, this is pi in radian, this is 2 pi in radian, and so on, 3 pi in radian, 4 pi in radian, and so on and so forth. So the values this Ka can take, they are what? N pi, where n equals 0, 1, 2, 3, and so on and so forth. So these are the values Ka can take, n, which is the quantum number, principal quantum number, multiplied by pi. Pi is 180 degrees. That is pi rad. Pi radian is 180 degrees. So if this Ka equals n pi, it means K will be what? It means K will be n pi divided by A. So let me call this equation 8. I think I've, hold on, sorry, that will be equation 9. So K equals n pi over A. So if K equals n pi over A, then from our equation 8, you know, our equation 8 was psi of x equals the A sine kx, sine kx. So which can now be written as A sine K is n pi over A. Okay, x. So A sine n pi over A multiplied by x. So this is our wave function. Okay, so therefore the wave function psi equals A sine n pi over A x. Okay, so in quantum mechanics, when we solve the Schrodinger equation, so this is the first thing that we obtain, the wave function. Then we also obtain the energy E. The energy E. Okay, how do we obtain the energy E in this case? So well, this is still equation 10. Now to obtain the energy E, so when you are solving a bound state problem in the Schrodinger equation, you obtain the wave function and the energy eigenvalue. This is the wave function that we obtained in equation 10. How do you obtain the energy eigenvalue? If you recall, in equation, there is an equation that I ask you to keep. Equation 5, we said 2me over h bar squared equals k squared. So from equation 5, we had 2me over h bar squared equals k squared. And here we are getting k to be n pi over a. So it means k squared will be what? N squared pi squared over a squared. So if that is the case, it means we have 2m e over h bar squared equals n squared pi squared over a squared. If you make e the sum of the formula, it means we have e equals n squared pi squared h bar squared, right, over 2m a squared. So this is the energy again. So let me put this n, because we can have e0 where n will be 0, e1 where n will be 1, e2 where n will be 2. But so let me before I explain that, let me label this as equation 11. So we have solved the Schrodinger wave equation. Okay, we have obtained the wave function and we have obtained the energy eigenvalues. Now, what are the values this n can take? We have to look at the physics, okay, of that. Now, if we say n is 0, if we say n starts from 0, if this is 0, then sine 0 is 0. It means this psi will be what? Will be 0. So n equals 0 makes no sense. So it means what makes sense is for n to start from 1, 2, 3, 4, and so on and so forth. Okay, so this n does not start from 0. So the lowest energy, okay, the lowest energy is E1. That is when n equals 1. That is lowest energy. This lowest energy is what we refer to as the ground state energy. Okay, so the lowest energy is called the ground state energy. Okay, the lowest energy is called the ground. So it is the lowest energy, okay, a system can have. So the lowest energy this system can have. So for this particular system, so for this potential, okay, the lowest energy is E1, which equals, so n will be 1 pi square h bar squared over 2m a squared. So that is the lowest energy it can have. So this is the ground state energy for the infinite square well potential. So this potential is called the infinite square well potential. Alright, so we have come to the end of the solution of the Schrodinger equation for this infinite square well potential. Alright, so let me show a plot of the wave function. That's this a sine n pi over ax. Let me show you a plot so that you see how you visualize the wave function. So I've written a simple, very simple Python script here. So recall, let me write the wave function here. I'm sorry. Psi of x equals a sine, I think is n pi. So n pi over a then x. So let me use left here so that it can be properly written. Okay. So this is the wave function a sine n pi over ax. So if we set a to be 1, capital letter A to be 1, small letter a to be 3, so the principal quantum number n can have value n equals 1, 2, 3, 4, and so on and so forth. So let's just take a range of x value from 0 to 3. So here x is from 0 to 3. Okay, and this is our psi. So a sine n pi multiplied by x divided by small letter a. So I will plot the wave function. So this is wave function if n is 1, principal quantum number is 1. So this is what we have. If we change it to 2, if we change this n to 2, it will change. That's another state. If we change it to 3, it will change. That's another state. Okay, and so on. So that is a visualization of the wave function. But this wave function does not tell us anything. It is the square of the wave function that tells us if something. So the square of the wave function is what I've plotted here. So let's start from 1 as well. So if you square psi, so this is what you get. Now I told you that the square of the wave function, so this is density. So this is rho, so which equals psi modulo psi squared. So modulo psi raised to power 2. So psi rho equals modulo psi squared. So what does this mean? What does this tell us? This is the probability density. If you look at this graph, at this point x equals 0, the density is 0. It means the particle cannot be found at x equals 0. And at x equals 3, the particle can also not be found there because the density, the probability of finding the particle there is what? Is 0. But if you look at x equals 1.5, the density, probability density is 1.0. So the highest probability of finding the particle anywhere is found at x equals 1.5. So it means the probability of finding the particle at 1.5 is what? Is 1. Okay, is 1, which is that amplitude. So if you change this n principal quantum number to 2, then you have another graph. So here the probability of finding the particle is very high at this point, which is around maybe 0.75. At 1.5, at x equals 1.5, the particle cannot be found there. The probability density is what? Is 0. At 0 it's 0, at 3 it's 0. So the particle has high probability of being found between 2.25 and 0.25. And the same thing if you change it to 3. Okay, I have another graph. So you have high probability of finding the particle at 0.5, at 1.5, and at 2.5. Okay, so this is where we stop today. See you next time.